This is mathheals.com, where you can find more links to math YouTube videos. Let's take a look at exponential functions. And this is just kind of refreshing your memory from college algebra, in case you need it. Hopefully this is all just review. They give it kind of a really light version of it in this section, just to dust off the cobwebs. Now remember, if you have x to a power times x to a power, then you're going to add your exponents. Now you can have anything here. You can have numbers, so you could have 2 to the m times 2 to the n, just as long as they're the same. Now we also have where you're raising one exponent to another exponent, and that's where you multiply them together. If you have something to the 0 power, that's always 1. If you have a negative exponent, like this right here, well, we want to write it in fraction form, so I put that over 1. And you take the part with a negative exponent opposite of where it's at in the fraction, and the sign of the exponent changes. So the x to negative 1 I take down to the denominator, and it becomes x to the positive 1. Now if and this is just, I'm doing these by example. Now here, if I have a negative exponent, it's already down in the denominator. Well, again, you take it opposite where it's at, so this x to the negative 2, I take up on top, put in the numerator, and it becomes x to the positive 2, like that. So again, to make it positive, you just move it opposite where it's at in a fraction. Now if we have a fraction to a negative power, let me actually put a number here, it'll mean more, like this here. So if we have x over y to the negative 3 power, you can flip a fraction, I don't know where that came from, take a reciprocal of it, and the sign of the exponent changes to positive. So x over y to the negative 3 becomes y over x to the positive 3. Now, some books actually will put versions of this in here, and I don't really like it, how they do that. So I'm just going to kind of generally write this. This is where everything inside the parentheses is either multiplication or division. So everything's being multiplied or divided. So everything inside parentheses is either multiplication or division. Then what you do is you take everything to that power. Now, what's popular is that they'll put like this right here. I've seen that in books, and there's different versions of it, where you got this times this to a power, and then you take the x to that power, and you take the y to that power. But it's a lot more than that. If everything is either multiplied or divided inside, no matter what it looks like, then you take everything to that power. Now if you have a plus or minus in there, then that screws it up. Now this one, I'm going to put an example here. This is where you got x to a power over x to a power, or y to a power over y to a power. These are the same anyway. What you do, and they give you formulas for these, but I don't like them, is you subtract the smaller exponent from the larger one. And you have x to that power where the larger exponent was. So again, you subtract smaller exponent from the larger one, and you have x to that power where the larger exponent was. Let me actually work this example just so we see what in the world I'm talking about there. Okay, we got x to the third over x to the fifth. Well, we'll subtract a smaller exponent from the larger one. So we got 5 minus 3 gives us 2, and we'll have x to the second power where our larger exponent was. Larger exponent was downstairs. So we'll put that in the denominator. And then you put a 1 here as a placeholder. Now, most formulas will give you like x to the m over x to the n is equal to x to the m minus n. And yeah, that's workable. But this is a much easier way to solve these problems. Now, there's some other exponent properties, but those are ones we'll take a look at, and we may run across some more while we're working these problems. Okay, we have 2 squared times 2 to the third. Well, up above, we said if you have these the same, these are both 2, then you add the exponents. So this becomes 2 to the 2 plus 3, which is 2 to the fifth. And I'm not sure if they're actually wanting us to solve them, but I will. 2 to the fifth is 32. Now B. Got 2 squared times 2 to the negative 4. Well, we said that if we have a negative exponent, you take it opposite where it's at in a fraction. Well, in order to do that, you have to have a fraction. So let's go ahead and create one. You can always create a fraction just by putting it over 1. Now, the part with the negative exponent, we're going to take opposite of where it's at in a fraction. So the 2 to the negative 4, I'll take down to the denominator. And it'll become 2 to the positive 4. Well, we said if you have, I said x up above, but it can be anything. If you have 2 to the power over 2 to the power, you'll subtract a smaller exponent from the larger one. So 4 minus 2 gives us 2, and we'll have 2 to that power where our larger exponent was, which was on the bottom. And 2 squared is 4, so our answer is 1/4. Here we have 2 squared to the third power. When you're raising one exponent to another exponent, you multiply them together. So that'll be 2 times 3, which gives us 6. And 2 to the 6 gives us 64. And then 2 to the negative 4. We don't want a negative exponent, so we move it opposite where it's at in a fraction. Well, it's got to be in a fraction to do that, so I'll put it over 1. You can always create a fraction by putting it over 1. Now the 2 to the negative 4, I'll move down to the denominator. And when I move it down below, it becomes 2 to the positive 4. Anytime you move anything opposite of where it's at in a fraction, the sign of the exponent changes. Well, 2 to the fourth is 16, so our answer is 1/16. And let me save that. This is exponential functions. There we go. Let's look at our next example. We have 2 squared over 2 to the fifth. Well, we've said if you got 2 to the power over 2 to the power, you subtract a smaller exponent from larger one. So we got 5 minus 2 gives us 3, and we'll have 2 to the third power where our larger exponent was, which was down below. And then we put a 1 there as a placeholder. You always put a 1 in the other place as a placeholder. Now 2 to the third is 8, so our answer is 1/8. Here we have 1/2 to the negative 3 power. And we said if you have a fraction to a negative power, you flip the fraction, so it becomes 2 over 1, and the sign of your exponent changes, so it becomes positive 3. 2 over 1 is 2, so that's 2 to the third, which gives us 8. Now here we got 18 to the 1/2 times 2 to the 1/2. Well, since I didn't write down this property, but if they both have the same exponent, what you can do is you can multiply them together and take them both to that power. So multiply 18 times 2, put it inside of parentheses, and raise that to the 1/2 power. Well, 18 times 2 is 36. Now this one is probably easiest for us to put it back into radical form. So we're going to have 36 to the first power inside the radical, and then we'll have 2 as our index. Whatever number is in your denominator here, that's what goes in your index, this little slot in the front. Whatever number is up on top is what power goes right here. Well, index of 2 is the square root. So this would just be the square root of 36. And 36 is 6 times 6. And it's a square root, so our index is 2, so we're looking for a pair of somethings. Here's a pair of 6s, so those are going to come out as a single 6. Let's see, 81 to the 2/3, and then 1/3 to the 2/3. Well, again, they're both to the 2/3 power, so I can multiply those two together. So I got 81 times 1/3, and then raise that to the 2/3 power. You can do that when you have the same exponent. 81 divided by 3 is 27, I think. Now this is a property I didn't write down. You don't see it a whole lot. But this is where we're taking a number to a fractional power, rational exponent, where the numerator, the number on top, is greater than 1. What we do is we're going to rewrite this by taking the numerator. Let me write that a little bit bigger so you can actually see it. There we go. We'll take the numerator, the 2, put it on the outside of the parentheses. Now 27 to the 1/3 is the cube root of 27. Remember, your denominator, the 3, is what goes in this little slot here. That's your index. The power, the 1, is what goes inside with your 27. Of course, 27 to the first is just 27. Now the cube root of 27. 27, prime factorization of it is 3 times 3 times 3. Now our index is 3, so that means we're looking for a set of 3 of something. Well, here's 3 3's, so those 3 3's are going to come out in front of the radical as a single 3. So we have 3, and then the second power remains, and 3 squared is 9. And let's look at the next problem. Let's see, 3a. We've got 3 to the 12th over 9 to the 8th. Now the only time our property works is if we have like 3 to a power over 3 to a power, or 9 to a power over 9 to a power. Different ways you could work this particular problem. One way it jumps out at me is the 9 I can rewrite as 3 squared. And then the eighth that still remains there. So we got 3 to the 12th over 3 to the 16th. You're raising one exponent to another exponent. You multiply them together. And now we have 3 to a power over 3 to a power. Subtract a smaller exponent from a larger one. 16 minus 12 is 4. And we'll have 3 to the 4th where our larger exponent is, which is down below. And then we put a placeholder of 1 up above. Well, 3 to the 4th is 81. So our answer is 1 over 81. Now B. We have 4 to the 4/5 times 2 times 2 to the 2/5. Well, if they were all 2 to a power, I could add the exponents. So that's what I want to do, is I want to rewrite them as 2 to a power. Now 4 is 2 squared. So I can go ahead and do that. And of course 2 is 2 to the 1st. And then this is just 2 to the 2/5. When you're raising one exponent to another exponent, you multiply them together. 2 times 4/5 gives us 8/5. So we've got 2 to the 8/5 times, and I want to get a common denominator. Since these both are going to have 5s, I want this one to have a 5. So I'll rewrite the 1 as 5 over 5. And now they're all 2 to a power, so I can add the exponents. So I got 8/5 plus 2/5 is 10/5, plus another 5 is 15/5. And 15 divided by 5 is 3, so we got 2 to the 3rd, which gives us 8. Let's see. Let me do it down here. 16 to the 1/2. 4 to the 3rd. And then all of that is to the 1/2 power. Well, kind of using the same trick as we have been doing. I see the 16 and the 4. I can rewrite 16 as 4 squared. So that's 4 squared. And the 1/2 power remains. Times 4 to the 3rd to the 1/2. Well, here I'm going to raise one exponent to another exponent, so I multiply them together. 2 times 1/2 gives us 2/2 or 1. So this is like 4 to the 1st times 4 to the 3rd to the 1/2. Well, 4 to the 1st times 4 to the 3rd, you add the exponents. So that gives us 4 to the 4th raised to the 1/2 power. Now you're raising one exponent to another exponent, you multiply them together. So that's going to give us 4, and then 4 times 1/2 gives us 4/2. 4/2 is 2, and 4 squared gives us 16. And let me do D right here. So we've got 9 squared times 27. Now obviously I'm not going to be able to rewrite 27 as 9 to a power. But I notice that 9 is 3 squared. So I can rewrite that as 3 squared, and then the second power right here still remains. And 27 is 3 to the 3rd. So then you raise this exponent to this exponent, you multiply the exponents. 2 times 2 is 4. And that carries down. Now we'll add the exponents. 3 plus 4 is 7. I'm just thinking there's no way I'm going to be able to do that one. So let me go to my calculator. Okay. If you're in something, go ahead and exit out by doing second mode. You can press clear to clear your display. And we got 3 caret 7. 2001.87. Now, I know you could take 9 squared is 81, take that times 27, and it seems like, well, that'd be easier. The goal here is to get comfortable with these properties. So that's what they're indicating. Let me save that page. And let's look at our next problem. It says sketch the graph of the function. Well, if I was doing it by hand, it's as simple as plotting points. Like I start with -2, -1, 0, 1, 2. Probably won't do much good to go above that. Then we take each one of those x values and plug them in for x there. So we got 3 to the -2, which is 1 over 3 squared. Remember, you take a negative, something with a negative exponent opposite of where it's at in a fraction. So we take it downstairs. And that becomes 1/9. This one would be 3 to the -1, which is 1 over 3 to the first, which is 1/3. This is 3 to the 0. Now remember our properties. Anything to 0 power is 1. This is 3 to the first, which is 3. And this is 3 squared, which gives us 9. So let me start out with 0, 1. So 0, 1. Right there. Then we have 1, 3. So be right there. 2, 9. Which is right there. Then -1, 1/3. Maybe right there. And -2, 1/9, which is even closer to the x-axis. So our graph would look like that, and then it skims that x-axis, getting closer and closer to it, but never touching it, never crossing it. That's actually a horizontal asymptote. You got a horizontal asymptote of y is equal to 0. Because when you think about it, see when I start plugging in all these numbers, no matter what, it's never going to equal to 0. 3 to the 0 is equal to 1. Start putting in negative ones here, it just becomes smaller and smaller. Now, to do this on your calculator, what we'll do is we'll press our y equals to go in graph mode. I have extra junk there from before. Let me clear all that out. Okay, now let me start over. Okay, so you're going to go into graph mode, so you press y equals. Press clear to clear out wherever's not a line. And then we'll do 3 and then caret x. And then graph. And again, you have to understand about exponential graphs, how they never just stop like that, keeps going forever. Just skims the x-axis. But that would be our graph. Number 5. We got f of x is equal to the x minus 3 plus 1. And I could graph y is equal to 2 to the x and then use our shifts. Remember, if your number's at the end, it's up or down, so this is up 1. If the number is inside with the x, and it's left or right, opposite what you'd think. The -3 would make us think it goes left 3, so it's really right 3. Now I'm just going to plug these in the calculator. I don't think there's a whole lot of value for you seeing me build a t-chart. So I'm going to press my y equals, press clear. I'll put in 2 caret, and I'll put a beginning parentheses, and then x minus 3, and then a closing parentheses. Now, anytime you're you got more than a single variable, single number up in your exponent, you have to put parentheses around it. So that's why I'm putting parentheses around x minus 3. And then I put in plus 1, and then graph. And that gives us our answer. Now let's sketch it. Not great, but I'm not very good at sketching those. Now, some of you have a newer TI-84. If I'm going to mode myself. What you'll see is, what will you see? Go to math print. What you'll do is when you go to y equals and you press clear and you put in your 2 and then you go to put in your x minus 3. You'll do a caret and it throws you in exponent mode. So then you do x minus 3. You press your right arrow key to get out of exponent mode and then you put your +1 in. And then graph. That only occurs on the newer TI-84s and above that. Now, if you don't want that to be that way, you want it to appear like everything else I kind of type in. If you go into mode, if you press mode, down arrow to your second page, and where it says math print and classic, you want to right arrow over, put your flashing cursor on the classic, and press enter one time, and then do a second mode. And now it'll be like how I enter it each time. But anyway, that's how you put in your calculator. I'll grab a drink here and we'll look at the next graph. F of x is equal to 3 to the negative 1/2. Try it again. Negative 1/2 x to the third, not x squared. Negative 1/2 x to the third. And it says sketch it. And again, I could build a T-chart and spend quite a while on it, but we'll just plug in our graphing calculator. Press y equals, press clear. Then we've got 3. We'll do caret. Remember, when you have more than a single number or a single variable in your exponent, you have to put parentheses around it. So when I plug this in, I want to put a beginning parentheses, then negative 1 divided by 2, then my x, and my caret 3, and then closing parentheses, and then graph. Later on, we'll get use calculus to find the actual graph of these instead of just sketching it like we're doing. Now this they never just stop. So this actually keeps going that way. So that's our graph. I got a lot of people don't understand exponential growth. I mean, it's pretty easy to see here. I got a graph. Let me see if I can locate it. National debt. I like showing this one because it shows exponential growth. Sorry, pretty good. Now this is the national debt. And I haven't updated this. I can't remember the last year, but last 2 or 3 years I haven't updated it. But you're going to see it keeps growing up. Now over here is Truman. A lot of people don't know when we first got in debt. That was our first president, was Washington. As weird as that seems. But if you think about it, you're starting out a country, you don't have any money. So you got to have money to get started. And there was one president that got us out of debt. I had a student one semester that knew that, and I can't even remember who it was. You'd think that'd be real famous. You'd think there'd be statues to that person, but I guess not. And then you see Eisenhower, Kennedy, and so forth. And and here's World War II, and in Korea, Vietnam, so forth. Hits on Ford, goes up a little bit. Carter goes up a little bit. Hits Reagan, goes way up. And then Bush Sr. comes in, and it goes way up. Hits Clinton. Clinton about levels it off. Unreal what he did. And then Bush Jr. took over, and it skyrockets. Obama takes over, and it skyrockets. Now, a lot of people try to interpret these, and you can. There's a lot of different factors here than what I'm saying. But when you look at this, people look at the Bush Jr., and they look, well, there's the wars for you. That's what happens when you get into wars. Well, that's not necessarily true. If you think about what's happening over here, we're just like blowing up Japan. We're rebuilding it. Germany, so forth. Korea. We got a war in Korea. Vietnam. Not even little blips. Now, granted, the inflation and they also paid for wars differently in some cases. Like in World War II, they sold war bonds, and there's different items. But war by itself does not increase it like that. People see Obama taking over here, and they say, well, there you go, there's Obamacare. And I can't believe that people are saying that even before Obamacare took effect. It's just like, you're an idiot. It hasn't even took effect yet. Wait till it takes effect before you blame it. What causes this is exponential growth. Goes slow, and then all of a sudden, overnight, it seems like it'll fly out of sight. That's just the nature of exponential graphs. If you look at our pictures here, what does that look like? Slow, boom, flying out of sight. Slow, boom, flying out of sight. Boy, my graph there looks pretty poor. This is actually it right here. This is my x-axis right here. But again, that's just the nature of exponential growth. When you start owing so much and you're paying so much in interest and it keeps accumulating, keeps growing and so forth, it'll fly out of sight like that. It has nothing to do with wars. I mean, well, a little bit, but that growth comes from just the nature of an exponential graph. Obamacare isn't what did this. That's just the continuing nature of it. Now, what Clinton did is he did something kind of radical. And he about got this leveled off. Then he could have got it to go down. So it was unreal what Clinton did. Now, Clinton wasn't necessarily that smart of a man, but he surrounded himself by financial geniuses, and that makes him a very, very smart president. Now, a lot of people don't understand where this national debt comes from. Well, at first, during the Reagan years, Reagan was the big one that raided Social Security. The idea of Social Security is you have all of your citizens pay into it, and then only the interest goes out to pay your retirees. So you have this huge amount of money that keeps growing and growing, and the interest keeps growing and growing, and it handles all future generations. Fantastic plan. My dad worked for Boeing, and they had a similar plan, and they didn't screw theirs up, or at least they didn't while he was working there. And all the interest went to pay all the retirees, and they got good medical, everything. Now they sold part of their business off, and they sometimes when they do that, they raid those accounts, which destroys them. And what Reagan did is when he started borrowing from Social Security, he destroyed it. I had to take my dad to every political meeting there was during that time, and it's just like I got tired of hearing it. But my dad ranted and raved, and I now understand why he did, because it destroyed it. When you start taking away that principle, it no longer has this huge pile of money, so that it can accumulate interest. Now he put a bunch of IOUs in there type of deal, but IOUs don't accumulate interest. And Bush Sr. kind of continued that. And I wouldn't say Clinton did any better. He probably still raided Social Security too. At some point, the money kind of run out in Social Security, and I mean that huge pile of money, and they started borrowing from the Chinese. And they claim by the year 2025 that the amount of interest that we're paying China, interest alone, by 2025 will fund their entire military. That tells you how this is growing. Now, the only way for this to change is for something radical to happen. You got to do something like what Clinton did. He raised taxes. Not very popular, is it? And he also cut a lot of different areas. He cut some military. He cut a lot of other areas. You got to have the two. You got to raise taxes and you got to cut people hard. That's the only way you can do something dramatic to change this exponential growth. And a lot of people don't seem to understand exponential growth. They just like to blame the other party instead of realizing what's really happening with that, which is unfortunate. But anyway, that's exponential growth. Let's take a look at our last problem, see what's asking for. We got S of t is equal to 30 times 1.143 t. And it says the sales S in millions is given by this model. And T is the time in years since year 2010. Now part A says use the model to estimate sales in 2015. Well, this is the beginning of time is 2010. And so T is the time in years since 2010. So in 2015, 5 years have passed. 2015 minus 2010. So we're going to plug 5 into that. So we'll have S of 5 is equal to 30 times 1.143 to the 5th power. And I want to exit out of graph mode, so I'll do a second mode. And we got 30, beginning parentheses, 1.143, closing parentheses, caret 5, and then enter. And we get 58. Probably doesn't say how many decimal places, does it? Take it to 2. 58.53. Now this would be, it's in millions, so that's our sales in millions. So 58 million, 58.53 million to be precise. Now on B, it says use the model to estimate sales in 2025. Well, if I take 2025 minus 2010, 15 years have passed. And so we'll plug in S of 15 equals 30 times 1.143 to the 15th power. And so I got 30, beginning parentheses, 1.143, closing parentheses, caret 15, enter. And we got 222.75 million. So those would be our two answers. And that's actually the end of that section too. So let me go ahead and stop the recorders. Actually, I better save that while I'm thinking of it. Sometimes if I don't go ahead and save that, then I forget and lose that page.